Okay, good evening, ladies and gentlemen. This is Professor David J. Del Reyes. I will be discussing tonight a long video format topic, and this is a continuation of my DC circuit long video topic, and I am now on lesson number 13. Okay, let's proceed. The subject matter for this evening will be direct current circuit, and this is now lesson number 13. This is a continuation of my long video format topic, direct current circuit. So for those of you who are taking up or intend to take up electrical engineering, this is for you guys. Or for those who would like to learn DC circuit, this is also for you guys. Okay, let's proceed. The title of the topic for this evening will be Norton's Theorem concept. Okay, this will be a concept on how to solve for a current in a given RL load if that load is connected to an active network. So in here it seems we are given an active network. Hold on. This could be the active network. Active network is actually a network that contains a voltage source and some resistances inside. And the two terminals are actually available. Like this one here. This will be the active network. And this is the existing terminal. Okay, this is an active network. It contains a voltage source and some resistances inside. So it's a live circuit. The two terminals are actually brought out. The problem here is that if we try to connect a load RL here for this active network, which contains a voltage source and some resistances inside, the problem is asking what will be the load current equal to. How could we compute? So for this afternoon, we will be discussing the concept on how to compute for this current here by using Norton's Theorem. Okay, Norton's Theorem. So in here, the requirement is what will be IL for that RL using Norton's Theorem. Okay, there are actually 3 steps on how to bring out the concept of a Norton's Theorem solution. Okay, let's try to bring out the solution. Step number 1. Step number 1. Disconnect RL. Short the terminals. The terminals should be plural. Okay, short the terminals. Then find the value of capital letter I with the subscript C. This is actually termed to as the short circuit current. This SC here is a subscript and this is capital letter I. So if we try to read this one under Norton's Theorem, this is the so-called short circuit current. That is step number 1. Okay, I will try to get my eraser. Excuse me. Because I want to draw something here. So step number 1, disconnect RL. We will remove RL. Right? Then it says we short the terminals. Okay? Then find for the short circuit current. If we short the terminals, okay, there should be a red marker here. We will be taking the value of the short circuit current equal to. That's step number 1. You disconnect the load, then you short the terminals, then compute or find for the value of the short circuit current. And how could we compute for the value of the short circuit current? And the actual thing, we will be getting our, what you call this multimeter here. We set it on the ampere range. If it's DC, we'll just change the mode to DC. Then we'll try to connect the first terminal here and the second terminal. So this is an active network. It got a voltage source and some resistances inside. So when we connect the multimeter here, there should be a what you call this, a current reading. And that current reading is the so-called short circuit current reading. Okay? That is in the actual thing. But how could we compute for ISC? What you call this, theoretically, by using our computation. In the computation of this ISC here, we will be recalling our knowledge on the concept of the series parallel theories, and we will apply it on the computation of IC. Okay? So for step number 1, we could do that. For the meantime, I could not show you the steps because we haven't got yet any problem. So just like what I said, step number 1, you disconnect the load, short the terminals, then compute for the short circuit current by using your knowledge of the series parallel combination concept. Okay? That's step number 1. Okay? So we are now done with this part here. This one. Actually, step number 1 is this part here. Okay? Step number 2. Short the voltage source. Sorry for this one. This should be with the T. Short the voltage source and solve for Rn. Rn is actually, capital letter R is resistance, and the subscript N is actually, this is Norton's. Okay? So if you try to read this one, capital letter R with the subscript N, we will solve R sub N, and the term for this Rn here is actually the open circuit resistance. Okay? But we must have to short the voltage source inside. Meaning to say, if you could see a voltage source inside, okay, and the computation of R sub N, we must have to short this one. Okay, so whatever resistances that will be left inside, okay, that will be termed as R sub N, but we must have to short any voltage source inside, meaning to say, after shorting it, it seems the voltage source is not present. So if the voltage source is not present, again, by using our knowledge of the series parallel concepts, we could compute for R sub N. Okay? For the meantime, I could not show you a computation for R sub N. Because we do not have an example yet. We are just discussing the concept. That's step number 2. And step number 2 is actually this portion here. This one. Okay? And how could we compute for the value of R sub N in the actual thing? Again, we will be using, again, our multimeter. We put it on the resistance thing, then try to connect the two terminals on here. Okay? But be sure that the voltage source inside is shorted out. Okay? Because you cannot measure resistance if there is a voltage source inside. And under the concept of Norton's, prior to the placing of the multimeter here on the ohms setting, you must have to short the voltage source. Okay, short. Okay, I will erase this one. We short it. Short the voltage source. That is in the actual computation, in the actual thing, right? But theoretically speaking, we are solving it theoretically. We will be using our knowledge of the so-called series parallel concept, but be sure that the voltage source is shorted. So actually, we could compute for R sub N. And that portion is step number 2 is actually this portion here. Okay? Step number 3. Draw the Norton's equivalent circuit. Okay, draw the Norton's equivalent circuit. The active network, we will be replacing it by its equivalent under Norton's from our computation of I short circuit and open circuit resistance as of N. And again, under Norton's, this short circuit source will be in parallel with the open circuit resistance. Unlike in the Thevenin's, the open circuit voltage is in series with the value of R Thevenin's. But under Norton's, this short circuit source will be in parallel with R sub N. So actually, these two combination here is actually the Norton's equivalent. Okay? The original terminals is actually on this portion. Okay? This is the original terminals. So after taking the Norton's equivalent circuit, in which the short circuit current is in parallel with R sub N, try to reconnect R sub L, where you reconnect it. Okay? So if you try to reconnect it, the short circuit current is computed already. The value of R sub N is already computed. Okay? We reconnect RL. Okay? So there should be a value for this one. So this is given. And the problem is now just asking what will be the value of I sub L equal to. Okay? Step number 1, this portion. Step number 2 is this portion. Step number 3, try to take the Norton's equivalent in which the short circuit current is in parallel with the open circuit resistance R sub N. Then try to reconnect the load. Okay, step number 4, this will be the last part. Step number 4, using voltage divider principle. Okay? It is something like this. I place it here. B sub N is equal to B sub L. The voltage across this, R sub N, is same as the voltage across R sub L because they are in parallel. That's why I place it here. B sub N is equal to B sub L. Okay? Meaning to say that, you try to place your voltmeter here. Okay? And try to place your voltmeter here. The reading should be the same. So the equivalent of that in terms of the formula, it will be V sub N is equal to V sub L. Okay? Voltage is equal to IR, right? Okay? So considering the voltage across this, it will be the current entering Rn, okay, times R sub N. And the current entering Rn is actually the total short circuit computed current minus I sub L. So it will be the difference I short circuit minus I sub L times R sub N. That is B sub N. And B sub L, okay, the voltage across this will be the same as this. That's why Bn equal to B sub L. And B sub L is actually the product I sub L times R sub L. So this is I sub L, R sub L. And if we try to simplify this, okay, ISCRN minus ILRN equal to ILRL. Then we'll try to place this one on the right. So it will now be plus, right? And this will be an equality. This is now plus because we transpose it on the right. So this is with the plus sign. Right? The common factor is I sub L. So this is I sub L. That's algebra. Times the quantity Rn plus Rl close quantity equal to. The left hand side, we just rearrange it. We put it on the right. I short circuit times R sub N. This is step number 1. The value computed from step number 1. This is the value computed from step number 2. Right? So if we try to compute for R sub L, R sub N is computed. R sub L is given. These two are given, so we could compute for I sub L. I sub L now, for a Norton's equivalent circuit, it will be the product of step number 1 times step number 2 all over the sum, Rn plus Rl. That will be our answer. That's the magnitude of I sub L. Okay? To check the veracity or truthfulness of this concept here, we will be solving a problem from the previous lesson. It will be the same as we will be solving the same problem for this. Because the next lesson will be lesson 14. I will be getting the previous problem and I will try to compute for the value of I sub L by using Norton's concept. And the answer should be the same as from the previous solutions. Okay, good afternoon from Los Angeles. This is Professor David J.